we're given the function f, and it is defined by a x to the power 3 plus b x to the power 2 plus c x plus d. And we're supposed to solve for a, b, c, d, the coefficients of this function. And at the same time, I am given 4 pieces of information. So we are going to make use of these 4 pieces of information to form 4 equations. And through that, hopefully we can solve for the coefficients a, b, c, d. So the first piece of information is that the graph of y is equal to fx is going to pass through the point 1, 5, which means that f1 is going to be equal to 5. When x is equal to 1, y, which is fx, is going to be equal to 5. So f1 is equal to 5. If I were to substitute 1 into the expression for fx, we will get a 1 to the power of 3 plus b1 square plus c times 1 plus d. This is equal to 5. This gives me my first equation. That is a plus b plus c plus d. This is equal to 5. Equation number 1. The graph is also going to be passing through the point -1, -3. I'm going to make use of the same idea. So f minus 1, this is going to give me a -3. So we will have a minus 1 to the power of 3 plus b minus 1 to the power 2 plus c times of -1 plus d. This is equal to -3. We will get an equation minus a plus b minus c plus d. This is equal to -3. This is my second equation. And the third equation can be formed by making use of the information that the graph has a turning point at x is equal to 1. So turning point, the feature of a turning point is when dy dx f prime x is equal to 0. So let's find f prime x or dy dx. So fx is given to me as ax to the power 3 plus bx squared plus cx plus d. So f prime x is going to be equal to 3ax squared plus 2bx plus c. D is a constant, so d is going to disappear. And since it has a turning point at x is equal to 1, so we know f prime 1, turning point, the gradient is going to be equal to 0. So f prime 1 is equal to 0. So substituting 1 into here, we have a 3a times 1 square plus 2b times 1 plus c. This is equal to 0. This will form for me equation number 3. And for the last equation, I'm going to form by making use of the integral that is given to me, 0, 1 of fx dx. This is given to me to be equal to 6. So integrating from 0 to 1, fx, this is ax to the power 3 plus bx squared plus cx plus d. So this is equal to 6. Let's integrate this. We will have ax to the power of 4 over 4 plus bx to the power 3 over 3 plus cx squared over 2 plus dx. And with a lower limit of 0 and an upper limit of 1, this is equal to 6. Substituting 1 in, we will have a1 to the power 4, and that will be a over 4. Then b1 to the power 3, this is going to be equal to b to the power 1 to the power 3 is going to be 1. So b over 3 plus this will be c over 2 plus d. And it will be this minus away when x is equal to 0, 0, 0, 0, 0. So when I substitute 0 into here, it's going to give me a 0. This is equal to 6. This gives me my fourth equation, and that will be a over 4 plus b over 3 plus c over 2 plus d. This is equal to 6. This is my fourth equation. I'm going to substitute this, and this into the feature that is in my graphing calculator to let my calculator solve for me these 4 sets of equations simultaneously, and they are linear. So I'm going to press it into my graphing calculator. So from my graphing calculator, I'm going to get the values of a is going to be equal to 4, b is going to be equal to -6, c is 0, and d is equal to 7. Let's take a look at the next question. So in question number 2, in part A, we are supposed to sketch both of the graphs that are given to me on the same axis. Let's first sketch the graph of y is equal to modulus of x squared minus 5. And I'm going to use the help of my graphing calculator. So based on my graphing calculator, this is the graph, part A. Let's say here is the y-axis. And let's make this the x-axis here. So based on my graphing calculator, the first graph is going to look something like this here. And with a maximum point here on the y-axis, coming back down, and here. And this is the graph of y is equal to modulus of x squared minus 5. So for this graph, if I were to let y be equal to 0, x squared minus 5, modulus of it is going to be equal to 0, so x is going to be plus or minus square root of 5. So this point here is going to be minus square root of 5, 0. And this point here is going to be equal to square root of 5, 0. And if I were to let x be equal to 0, y is going to be equal to modulus of minus 5, which is going to be equal to 5. So this point here will have a coordinate of 0, 5. Let's draw the other graph. The graph of y is equal to 2x minus 1. Again, I'm going to make use of my graphing calculator. And that graph is going to look something like this. From here, cut. And it is a straight line. This straight line is y is equal to 2x minus 1. When x is equal to 0, y is equal to minus 1. So this point here will have a coordinates of 0, minus 1. And when y is equal to 0, x is going to be equal to half. So this x-intercept here is going to be equal to half 0. This is part A. In part B, find the exact solution of modulus of x squared minus 5 is equal to 2x minus 1. So in part B, we are supposed to find the x coordinates of the intersection of the two graphs. And we can see from here that the x coordinates are both going to be positive. So let's take note of this. We probably will need to make use of this to decide on the answers to accept later on in our solution. So let's take a look at B, where modulus of x squared minus 5, this is going to be equated to 2x minus 1. So removing the modulus x squared minus 5, this is going to be equal to plus or minus 2x minus 1. I'm going to separate this into two separate equations. One will be x squared minus 5 is equal to negative of 2x plus 1. Negative of 2x minus 1 is going to be negative of 2x plus 1. The other one is going to be when x squared minus 5 is going to be positive of 2x minus 1. Let's try to solve this first. I'm going to shift everything over to the left-hand side. So this, we will have a x squared plus 2x minus 6 is equal to 0. To solve for x, let's make use of the quadratic formula. So we have a minus b plus or minus square root of b squared. So 2 squared minus 4ac. So this divided by 2 times of a, which is 1. The coefficient of x squared is 1. And this gives me a minus 2 plus or minus square root of 28 over 2. And please take note, we have talked about it just now, we are going to be accepting only positive answers from here because based on the graph, the x coordinates of the intersection of the two graphs is going to give me the solution to this, and the x coordinates of these 2 points are positive numbers. So this is going to be equal to, if I were to just simplify this, this is going to be equal to minus 1 plus or minus square root of 7. And since we are accepting only the positive one, this answer is going to be minus 1 plus square root of 7 because the other value is going to be negative. Okay, so this is because x is supposed to be bigger than 0 based on the graph. I'm going to solve for this. I'm going to bring everything over to the left-hand side again. So x squared minus 2x minus 4, this is equal to 0. Making x the subject, making it by using the quadratic formula, this is going to be equal to minus b plus or minus square root of b squared minus 4ac. So this divided by 2a, this will be 2 plus or minus square root of 20 over 2. Simplifying this, we will get a 1 plus or minus square root of 5. Again, we are going to be choosing just a positive value. So this is going to be equal to 1 plus square root of 5. And again, I'm doing this based on the fact that x must be a value that is bigger than 0 according to my graph. That's it for question number 2. I think it is quite an okay question. Let's take a look at the next question, question number 3. Okay, question number 3 is a calculus question. So far, I think question number 1 and 2 are pretty simple. Let's see how challenging or how easy question number 3 is. So we're given that x to the power of 1 over 2 plus y to the power of 1 over 2, this is equal to 3. And in part A, we are supposed to show that equation, which is going to be dy dx, a first order differential equation. So we are going to try to differentiate this with respect to x, and hopefully we can show dy dx according to what the question says. So I'm going to differentiate this left-hand side with respect to x to the power half, y to the power half, and I'm going to differentiate the right-hand side with respect to x also. I mean, it is 3. So when I differentiate the right-hand side, it's going to be equal to 0. So on the left-hand side, differentiating this, we will have a half x to the power of minus half. Differentiating this, we are going to apply implicit differentiation. So it's going to be half y to the power of minus half dy dx. This is equal to 0. Let's bring this over to the right-hand side. So on the left-hand side, we will have a half y to the power of minus 1 over 2 dy dx. This is going to be equal to minus half x to the power of minus 1 over 2. We can divide by half on both sides. And I guess this we can also try to bring it to the bottom. This we can also try to bring it to the bottom. So we have a 1 over y to the power of half and times dy dx here. This is equal to, this is going to be 1 over x to the power of half. And let's not forget about the negative. Then I'm going to multiply this across to the other side. So based on this, dy dx is going to be equal to negative of y to the power of half divided by x to the power of half, which is going to be equal to negative y over x to the power of half. Okay, this is what the question wants us to show. And part B, we are supposed to find the equation of the normal to the curve at a point when x is equal to 1. Okay, not too bad. When x is equal to 1, in order for us to find the equation of the normal, we just need 2 more pieces of information. One is the value of y when x is equal to 1. The other one is the gradient of the normal, which we can derive based on the gradient of the tangent. So let's try to find this. So when x is equal to 1, I'm going to make use of this to find the corresponding y value. So when x is equal to 1, we have a 1 to the power of half plus y to the power of half. This is equal to 3. So y here is going to be equal to, y to the power of half here. Let me erase this. So y to the power of half here, this is 1, bring it over to the other side. This is equal to 2, which means that y is going to be equal to, squaring both sides, y is going to be equal to 4. Then we're going to try to find out what is the gradient of the tangent when x is equal to 1. So I'm going to make use of this. So that will be dy dx. dy dx will be minus y. Y we know it is 4. So 4 over x, x is equal to 1. So this to the power of half, this gives me a minus 2. So based on this, now we can find the equation of the normal when x is equal to 1. So it will be y minus the corresponding y coordinate, which is 4, is equal to the gradient of the normal. The gradient of the normal will be negative 1 over the gradient of the tangent. So minus 1 over minus 2 of x minus away the corresponding x coordinates of a point that is on the line. So it's going to be equal to 1. So from here, y is equal to 1 over 2x plus 7 over 2. This is the equation of the normal. Let's take a look at question number 4. Okay, question number 4. This question looks sort of intimidating. Let's give it a try anyway. So we're given this complex number, okay, the intimidating expression that is in front of us right now. We want to find out what is the modulus of z and the argument of z. Okay, let me write down this z first, the one that is given to us. So the question tells us that z is equal to cosine of 1 over 16 pi plus I sine of 1 over 16 pi. And this will be squared divided by the denominator is cosine of 1 over 8 pi minus I of, again, 1 over 8 pi. So for the numerator, I am going to convert it directly to the Euler form. I think as an Euler form, it is way easier for me to do power and stuff. Okay, so by default, I think it is just going to be a good strategy to try to change this into an Euler form, especially when I have a complex number to the power. So changing this to the Euler form, it is going to be e to the power of I of 1 over 16 pi. So we have this to the power of 2. I'm going to try to do likewise for the denominator, but for the denominator, this is not the trigonometric form that we are used to. The one that we're used to has to be a plus that is here. So in order for me to convert the denominator, which can also become an Euler form, provided that we change this into the more standard trigonometric form, we're going to make use of two trigonometric transformation, two that we have learned in our secondary school. One is this, cosine minus theta. This is the same as cosine theta. The other one is sine of minus theta. This is minus sine of theta. Okay, so I'm going to make use of these two that we have learned in our secondary school to apply to this and this. So for the numerator, it is going to remain the same. Let me just recopy this here. Cosine of 1 over 16 pi plus I sine of 1 over 16 pi, then square, okay? Because this is going to be converted to e to the power of I 1 over 16 pi. So that is no problem for the denominator. Cosine 1 over 8 pi. Cosine theta is going to be the same as cosine minus theta. So I'm going to convert this to cosine minus 1 over 8 pi. Then minus sine 1 over 8 pi minus negative theta is the same as negative sine theta. So this denominator here, this is going to become plus I sine of minus 1 over 8 pi. Okay, we are making use of this because this, according to what we have here, is going to be the same as minus sine 1 over 8 pi. So now in the denominator, we have the cosine theta plus I sine theta format. This is the trigonometric format, which will then allow us to rewrite the denominator into e to the power of minus I 1 over 8 pi. So we have now this, and I think it is going to be very easy for us to continue from this point onwards to try to combine all together to make z into one single Euler form. So this, in the numerator here, it is going to be e to the power of I. 2 multiplied by 1 over 16 pi will give me a 1 over 8 pi over e to the power of minus 1 over I 1 over 8 pi. And this will be e to the power of I 1 over 8 pi, e to the power of I again 1 over 8 pi. So ultimately z is going to be e to the power of I 1 over 8 pi plus 1 over 8 pi. Let me just write it down. So 1 over 8 pi plus 1 over 8 pi. This is giving me a e to the power of I 1/4 pi. So e to the power of I 1/4 pi is in the Euler form because we can definitely express this as if it is 1 multiplied by e to the power of I 1 over 4 pi. So the modulus of z is equal to 1 and the argument of z is equal to 1/4 pi. So now let me write it down. Modulus of z here is 1 and the argument of z is equal to 1/4 pi. So we have found modulus of z and argument of z, hence the question says we are supposed to find the value for z squared. So for z squared, what is the modulus of z squared? This is going to be equal to 1 squared. So the modulus of z squared, this is equal to 1. And how about the argument of z squared? This is going to be 2 times the argument of z. So this is going to be 2 times of 1/4 pi. This is equal to 1 over 2 pi, which means that z squared is going to be, let me express it in the trigonometric form, okay? So z squared is going to be equal to its modulus, which is 1. Then after that, cosine of its argument, which is 1 over 2 pi. Then plus I sine of its argument, which is also 1 over 2 pi. We can evaluate this. Cosine 1 over 2 pi is 0. Plus I sine 1 over 2 pi is 1. So in fact, z squared here is equal to 1 times I. It is equal to just I. Let's continue. Let's take a look at B. So for B, we are going to make use of probably some result from part A. But let's hang on first. Okay, let's just see what we have in B. B part 1, we are supposed to show this. We are supposed to show that cosine theta plus I sine theta multiplied by 1 plus cosine theta minus I sine theta is equal to that expression. In order for me to show this, I'm going to start with the left-hand side. So let me write down the left-hand side, which is cosine theta plus I sine theta. Then this is going to be multiplied to 1 plus cosine theta minus I sine theta. Okay, should we expand the whole thing without much planning? Of course we can. You just take this, multiply by this, multiply by this, and so on. Okay, but if you were to look at what we are supposed to be proving, maybe it is a good way for us to, maybe it is good for us to just reorganize what we have a bit first before we start our expansion. For example, okay, I can see a possibility of reorganizing this. For example, what if I were to just, okay, I'm going to leave this as it is first. As for this, I'm going to rewrite it as 1 plus, I'm going to group this together, cosine theta minus I sine theta. Okay, the reason is because I see this as A plus B and this is A minus B. So the expansion will be a bit simpler if you are able to come up with a bit of strategy, like for example this, so that I can take this multiply by 1, which will give me cosine theta plus I sine theta. Okay, and this gives me this part directly, okay, cosine theta plus I sine theta. And when I take this multiply by this, we will have a cosine theta plus I sine theta multiplied by cosine theta minus I sine theta. Okay, and we are achieving something that is more efficient here because we actually pause and think. And I think that is a very, very important thing that we are supposed to learn through H2 math, thinking. So this is going to be cosine theta plus I sine theta. How about this? A plus B multiplied by A minus B, it is going to be A squared minus B squared, but this is complex number with an I here. So if I were to apply what we have learned in complex number, it is going to be this square plus sine theta square. So we have a sine squared theta plus cosine squared theta, which is equal to 1. Let me write it down here. So this, according to trigonometry, okay, it's not even complex number now. According to trigonometry, this is going to be equal to 1, trigonometric identity. So now what we have is going to be a 1 plus 1 is from here plus this cosine theta plus I sine theta. Okay, then this is what the question wants us to show. Shown. Let's take a look at part 2. Part 2, we have this 1 plus z then to the power of 4 plus 1 plus z conjugate to the power of 4. I think this is definitely a question that we need to pause and think, because we are going to try to make use of this result. The fact that this is equal to this. And I think we are definitely going to be making use of the previous part because we are looking at z again. So let me just quote the result that we have obtained from the previous part. Okay, so from the previous part, we know that z was okay, the modulus of z, this is equal to 1. And the argument of z, we found that this was equal to 1 over 4 pi. So, okay, we can say that z is equal to 1e to the power of 1 over 4 pi. And we have also found that z squared is equal to I. Okay, so these are the two more direct results that we can retrieve from part A. Let's see what we can do based on what we know about part A and what we know about B part 1 to try to see whether we can evaluate this as quickly as possible. I think I am going to try to see z as I'm going to try to see z as this. Okay, so I'm going to try to see z as if it is cosine theta plus I sine theta. Because if I can do so, then this here is going to be like z. And this over here, cosine theta plus I sine theta is z. That means this over here is going to be z conjugate. So let me try to re-express this as z multiplied by 1 plus z conjugate. So it will be this to the power of 4 plus 1 plus z conjugate to the power of 4. And the reason why I'm doing this is because if I can do something that is like this, then we have a repeated expression here. And if I can expand this, we have a z to the power of 4. Then this is going to be 1 plus z conjugate to the power of 4. Then 1 plus z conjugate to the power of 4. And this allows me to factorize 1 plus z to the power of 4. So We have a z to the power of 4 here. Factorizing this is going to be leaving me with a 1. So factorizing this out from here and here, let me write it down here. This will be this to the power of 4. So we have a z to the power of 4, which we can actually evaluate. You know why? Because we know what is z squared. This makes it way easier for us to evaluate z to the power of 4 now. So this will be z square. Okay, this will give me z to the power of 4, then plus 1. So this, then 1 plus z conjugate to the power of 4, and it will be I square plus 1, then multiply by this. Let me just continue to write it as it is, this to the power of 4. And what is I square? I square is minus 1. So we have a minus 1 plus 1. Then after that, 1 plus z to the power of z conjugate to the power of 4. And what is minus 1 plus 1? It is 0. So 0 times this. My answer here is 0. Okay, done. This is question number 4. Let's take a look at the next one. Question number 5. Question number 5, part 1. We are supposed to carry out a process of partial fraction. So part 1, this is part A. So for part A, we are going to let what that is given to us, which is this x over x plus 2 multiplied by x plus 3 multiplied by x plus 4. We're going to let this be equal to a over x plus 2 plus b over x plus 3 and c over x plus 4. In order for us to find a, we are going to make use of the cover-up rule that we have been discussing. So to apply the cover-up rule, we are going to cover up x plus 2, and I'll let the rest of the x here be the value of x that caused the denominator of a to be equal to 0, and that is when x is equal to minus 2. So a is going to be equal to, letting the rest of the x be minus 2, divided by covering up this, not using this, focusing on the other two expression, minus 2 plus 3, and here minus 2 plus 4 gives me a to be equal to minus 1. For b, I'm going to be covering up x plus 3, and I'll let the rest of the x be equal to minus 3. So minus 3 divided by minus 3 plus 2. Then removing this, considering just this, minus 3 plus 4. b here is equal to 3. And let's find out what is c. c here is equal to, again, using cover-up rule, we are going to be covering up x plus 4. And I'll let the rest of the x be equal to minus 4, the value of x that caused the denominator here to be equal to 0. So we will have a minus 4 divided by minus 4 plus 2, then minus 4 plus 3. This will already be covered up. I will not be considering it. This is equal to minus 2. So therefore, we can now express this in its partial fraction. Let me just write it here, okay, so that I can create for myself some space later on. So a is going to be equal to minus 1. So this here is negative 1. b is equal to positive 3. So this here, b. b here is positive 3 and c is negative 2. Okay, now we have this being expressed as its partial fraction. I guess we will definitely be using this for the next part of the question, which is a summation question. Hence, the question says, okay, we are going to be making use of this result. So hence, the question says we are supposed to evaluate the sum from r is equal to 1 to n of r over r plus 2, r plus 3, r plus 4. Okay, it is exactly the same as this, except the x is being replaced by r. So let me just re-express this in its partial fraction based on what we have in part A. So this will become a minus 1 over r plus 2 plus 3 over r plus 3 minus 2 over r plus 4. Let's expand this and present it in the way that will allow us to experience the method of difference, okay? Because that is what I guess that can help us to evaluate this set of summation over here. So when r is equal to 1, so when r is equal to 1, we have a minus 1 over 1 plus 2, this is 3, plus 3 over 4, minus 2 over r is equal to 1, so 2 over 5. When r is equal to 2, so we have a minus 1 over 4, plus 3 over 5 minus 2 over 6. This is when r is equal to 2. When r is equal to 3, we have a minus 1 over 5 plus 3 over 6 minus 2 over 7. And we are starting to see a set of numbers that can be cancelled, which is this. Minus 2 over 5 plus 3 over 5 and minus 1 over 5. So my suspicion is that there is going to be a cancellation that is going this way. We want to affirm this by writing down one more row because we want to see a pattern of cancellation, not just a cancellation, not just one single cancellation. We want to see a pattern. So I'm going to let R be equal to 4, which will give us a minus 1 over 6 plus 3 over 7 minus away 2 over 8. And we do see that repeated cancellation, so we are starting to see a pattern. We're going to verify this by writing down the last set of values. 3 rows gives me 1 cancellation that is like this. So let me write down the last 3 rows too. So in between, I'm going to just let it be the third last row. The third last row is when R is equal to n minus 2. Let me write it down here. So this is when R is equal to n minus 2. And the other one, I'm going to go for R is equal to n minus 1. And the final one is going to be R is equal to n. Okay, so let's try this. So when R is equal to minus 2, we will have a 1 over n minus 2. When R is equal to n minus 2 plus 2. So it will be minus 1 over n. And then this will be 3 over n plus 1, then minus 2 over n plus 2. When R is equal to n minus 1, we will have a minus 1 over n plus 1 plus 3 over n plus 2 minus 2 over n plus 3. When R is equal to n, this will be minus 1 over n plus 2 plus 3 over n plus 3 minus 2 over n plus 4. And we are seeing exactly the same kind of pattern of cancellation being exhibited here because this, they are going to be cancelled away. So we can now imagine that in between, all the rest of the terms are going to be cancelled away in the same manner. So this will disappear and this will also disappear. What I'm going to be left with will be, let me write it down here, will be this minus 1 over 3 and then this plus 3 over 4 and this minus 1 quarter. And we're going to be left with this minus 2 over n plus 3 and this plus 3 over n plus 3 and this minus 2 over n plus 4. Doing a bit of simplification to this will give us our final answer as 1 over 6 plus 1 over n plus 3 minus 2 over n plus 4. Now let us move on to the last part, part C, which is actually a pretty easy part. It is trying to ask us about the sum to infinity of this. So let me rewrite this. It's going to be sum from R is equal to 1, and this time n here is going to be replaced by infinity. Sum to infinity from 1 to infinity of R over R plus 2, R plus 3, and R plus 4. Let's do a double check. Okay, so this expression here is exactly the same as this. So I can now make use of the previous result, and that is when n here goes to infinity. Let me write down the limits notation, which is not necessary. Okay, it is more of like for me trying to communicate to you a little bit of this n tending to infinity thing. So this line here is not super necessary in your solution. This is just a 1-mark question anyway. So it is the limit when n is going to tend to infinity. It is this n of the expression 1 over 6 plus 1 over n plus 3 minus 2 over n plus 4. So when n tends to infinity, this will become 0. This will become 0. So my final answer here is going to be equal to 1 over 6. Let's take a look at question number 6. Where in the first part, we are supposed to sketch the graph. So we will definitely try to make use of our graphing calculator, but we do have to make an assumption because the value of a is not given. So I'm going to let a be some positive value because the question did mention to me that a is bigger than 0. So I'm going to probably let a be, for example, 1, and I'll put it into the equation and I'll sub it into the graphing calculator to give me an idea of how the graph looks like. And based on the graph, I am suspecting, I mean, you guys should definitely press it to your calculator. If you were to look at it from the calculator, you should be suspecting that there's going to be vertical asymptotes. So before I sketch my graph, let us try to work out the vertical asymptotes. In part A, for vertical asymptotes, looking at the expression that is given to us, we will be letting the denominator be equal to 0 because vertical asymptotes are the values of x that cause y to be undefined. So I'm going to be letting the denominator, which is square root of 4ax minus x squared, I'm going to let this be equal to 0. So 4ax minus x squared, this is going to be equal to 0. If I were to factorize out x, then we will have a 4a minus x. This is equal to 0, which means that x must be equal to 0 or x must be equal to 4a. So these are the two values that cause the denominator to be equal to 0. So this will also translate to the labeling of the vertical asymptote that I'll be expecting on my graph. And I see that in my graphing calculator. Let me sketch my graph here. So if this here were to be the y-axis, and let me draw my x-axis here. So let's say this here, this is the x-axis. Let us draw the asymptotes first. Okay, I'm always telling my class it is always a good habit to draw all the reference lines first. So there are two vertical asymptotes. One is equal to 0. The other one is when x is equal to 4a. So x is equal to 0 is this y-axis here. X is equal to 4a, it is going to be here. So let me sketch it in here. Okay, so this is x is equal to 4a. And based on what I have in my calculator, I'm going to make sure that my graph tends towards the asymptote here. It will turn, and then it will turn back towards the asymptotes. So based on this graph here has a minimum point. Okay, this is the graph of y is equal to 1 over square root of 4ax minus x squared. Let's try to work out the coordinates of this minimum point. And because of a, I don't think I will use my calculator because what I have on my calculator is me assuming that a was 1. So I'm going to try to work it out manually, and that will require me to do a dy dx and letting dy dx be equal to 0 since this is a turning point. So let me write down y, and this time I think I'm going to write down y in this form. So this, we have a 4ax minus x squared to the power of minus half since we are going to be differentiating y. So dy dx, this is going to be equal to minus 1 over 2. Then 4ax minus x squared to the power of minus 3 over 2. Differentiating this, we have a 4a minus 2x. So we have this. Simplifying this will get us a minus of 2a minus x over this, which is going to be a 4ax minus x squared to the power of 3 over 2. We can leave it as this, or it really depends. Okay, I can also remove this negative by moving this negative into the numerator instead. So it is also okay if you were to have an expression that is like this: 2a divided by 4ax minus x squared to the power of 3 over 2. And since we are trying to work on the turning point, we are going to be letting dy dx be equal to 0. So letting dy dx here to be equal to 0, it is like letting x minus 2a over 4ax minus x squared to the power of 3 over 2 to be equal to 0. Okay, this 2 looks like a bit like 3. Okay, so it is 3 over 2. So I'm letting this be equal to 0, which means that the numerator x minus 2a is equal to 0. So x is going to be equal to 2a. My aim is to try to find the coordinates of this point. So when x is equal to 2a, I'm going to substitute it back into here to find the corresponding y. So when x is equal to 2a, y is going to be equal to 1 over square root of 4a multiplied by 2a minus away 2a squared. So y will be 1 over square root of 4a squared. This is equal to 1 over 2a. I mean, we can see this as a positive. We don't need to consider plus or minus. The reason is because I can see from my graph that we are getting a positive y coordinate, and a is positive. Okay, so x is equal to 2a, y is equal to 1 over 2a. This tells us that the coordinates of this point here is 2a and 1 over 2a. This will actually help us in part B of the question, because in part B of the question, we are supposed to find the smallest possible value of y in terms of a. And look at this, what is the smallest possible value of y? It is actually this, right? The y coordinates of the minimum point. So I'm going to write that down here from my graph. The smallest possible values for y is going to be equal to the y coordinate of the turning point here. It is 1 over 2a. As for C transformation, I don't think I will need this graph, so let me erase my solution here, okay? So for C, we are supposed to transform and map the graph of C. Let me write down. The graph of C looks like this. Y is equal to 1 over square root of 4ax minus x squared. So this is supposed to be mapped onto the other graph. The other graph which looks like this. Y is equal to 1 over 4a squared minus x squared. Square root, okay, and this really requires us to think a little bit. Okay, how will this be mapped to this? Which means that we are going to be making use of what we have learned in graphical transformation, specifically translation, scaling, reflection. So we don't want to deviate away from what that is within our syllabus, but obviously from what we are looking at in terms of the expression that is that are given to us so far, we can't really be using translation, scaling, reflection according to what we have learned yet. Okay, so we need to do a bit of improvisation and manipulation. And my suggestion is to try to change this because here there's only one x, okay, or at least one term here, which is the x square term. But here there are two terms, x and x square. We can actually combine these two terms together if we were to carry out a simple algebraic manipulation, and that is completing square. Let me show you what I mean. So based on this, I'm going to complete square to the denominator. To complete square to the denominator, we need to first make sure that the coefficient of x squared is positive. So I'm going to factorize out minus, which will give me an x squared minus 4ax. And this will become a 1 over square root of, okay, now we can complete square. So this will be x minus 2a squared minus 2a squared. So this is the half completed square form. And if I were to just expand this further, so this multiplied by this is going to be equal to 4a squared. And this multiplied by this is going to be this, x minus 2a squared. Now we are ready. If you were to look at what we have here, which is supposed to be changed into this, we just need to replace this x here by x plus 2a. Then this will become x, and x squared will be this x squared over here. So that's what I'm going to try do. I'm going to replace this x here. Let me indicate it properly. I'm going to replace this x here, okay? I'm going to replace this x here by x plus 2a. So that's what I'm going to do. So the new expression is going to look like this. 1 over square root of 4a squared minus away this x here. I'm going to use red color to let you guys know that I'm actually replacing this x, okay? So I'm going to be replacing this x here by x plus 2a. Okay, so then we will have a minus 2a here square. So y will now be 1 over square root of 4a square. Minus away this and this will be cancelled, x squared. So it is going to be what we are supposed to be mapping it to. So based on this transformation, we are replacing x by x plus 2a. So what is the transformation? The transformation will be a translation by 2a units. Since we are replacing x by x plus 2a, it is going to be a translation of 2a units in the negative x direction. So in the negative x direction. Okay, this is for the last part of this question number 6. Let's move on. The next one is, okay, question number 7. Question number 7, we are given that y is equal to e to the power of sine inverse x. In part A, we are supposed to show the equation. In part A, okay, we know this is a Maclaurin's question, okay, but part A that is given to us, it is more of like a differentiation technique question. And I think it is good for us to not just simply work on differentiation as a technique. We should also work on differentiation technique, but at the same time, we also want to make sure that we are able to improvise and strategize, like how we have discussed for the few parts that we have experienced in the previous questions. So what I'm going to do is, for what that is given to me here, I don't think it is so it is an equation that is friendly enough for us to differentiate it directly. So with a bit of thoughts again, and with me willing to carry out a bit of my own improvisation, to initiate my own improvisation, what I think I'm going to try to do is to ln both sides, which will give me a ln y is equal to sine inverse x, because I do think that this version is easier for me to differentiate. So from here, if I were to differentiate the left-hand side with respect to x, I'm going to be getting a 1 over y dy dx. This is going to be equal to 1 over square root of 1 minus x squared. And if you're to look at what you are supposed to be showing, I don't think I will want to leave this square root of 1 minus x squared in the denominator. Okay, because this is going to get sort of like complicated. So what I'm going to do is I'm going to just cross multiply. Okay, I'm going to multiply this across and y. I'll multiply across to the other side. So we have a square root of 1 minus x squared dy dx. This is equal to y. Again, I'm initiating some improvisation here, okay, which the question didn't tell me so, but we are trying to come up with a plan, a strategy that hopefully will work in terms of getting a more efficient set of solutions. So let's see whether our plan really works, okay? It works based on the fact that we are going to be deriving what we are supposed to be showing faster and more efficiently. So from here, let's try, okay? Let's try to differentiate it one more time. And let's see whether we will be able to get the equation that the question is asking me to show. So on the left-hand side, I'm going to apply the product rule. So square root of 1 minus x squared. I'm going to leave it as it is. Differentiating this is going to be d squared y dx squared. Then differentiating this now, it is going to be half 1 minus x squared to the power of minus half minus 2x. Then dy dx is equal to, this will be dy dx. And let's simplify this a bit first before we decide what to do next. So simplifying this, we'll have a minus x over square root of 1 minus x squared. Then dy dx, this is also going to be equal to dy dx. And now, if I were to try to multiply throughout by square root of 1 minus x squared, this will become the same coefficient as this, the coefficient of d squared y dx squared. So it seems like the strategy is still working. So let's continue. So multiplying this through this equation throughout by this square root of 1 minus x squared will give me a 1 minus x squared, then d squared y dx squared minus x dy dx is equal to square root of 1 minus x squared dy dx. So we have achieved this because this is what the question wants me to show. And we actually have this also, this x dy dx, which is going to be obtained the moment when I bring this over to the right-hand side. So let me do that. So we have a 1 minus x squared, then d squared y dx squared. Bringing this over to the right-hand side, it is x dy dx plus this over here. And according to what the question is asking for, this over here is supposed to be changed to y. Is it possible? Yes, it is possible, because if I were to just trace back to what we have, it is from here, where y is equal to square root of 1 minus x squared. And we have a square root of 1 minus x squared. So based on this is now going to be converted to y. And this is exactly according to what the question wants us to show. So I guess our strategy works well. Let's move on to B. B, we are now supposed to be finding the first 4 terms of the Maclaurin's expansion of e to the power sine inverse x. So we are going to be making use of the formula for Maclaurin's. We already have y. We already have an equation for dy dx, and we also now have an equation for d squared y dx squared. We need one more in order for us to derive the first 4 terms of the Maclaurin's expansion. At least one more, which is an equation for d cubed y dx cubed. So let's try to differentiate this. Applying product rule to this, we'll have a 1 minus x squared d cubed y dx cubed, then plus minus 2x multiplied by d squared y dx squared is equal to, again applying the product rule to this, this will be x d squared y dx squared plus 1 time of dy dx plus differentiating y with respect to x, it is still going to be equal to dy dx. Simplifying this, 1 minus x squared d cubed y dx cubed. This, I'm going to bring it over to the right-hand side to combine with this, which will give me a 3x d squared y dx squared. Then this, it will be 2 times of dy dx. Okay, now we are ready to come up with the with a part of the coefficients of the Maclaurin series expansion for the first 4 terms. So the coefficients, part of them will be obtained from letting x be equal to 0 and getting the value for y. Y is equal to e to the power of sine inverse 0. Sine inverse 0 is 0, so e to the power of 0, this is equal to 1. And I'm going to find dy dx. dy dx will be y divided by this. So it will be y, which is 1, divided by square root of 1 minus x, which is 0 square. So dy dx is also going to be equal to 1. d square y dx square. So d square y dx square. This is going to be equal to x, which is 0. Nice. So this plus y is equal to 1, divided by this, which is going to be 1 minus 0 squared. This is equal to 1. Let's find the last part of the coefficient, d cube y dx cube. So this is going to be equal to, again, 0, nice, plus 2 times of dy dx, which is 1, divided by 1 minus 0 squared. So this is equal to 2. Now we know the Maclaurin's expanded form for e to the power of sine inverse x. It is going to be equal to f0, which is going to be equal to 1, plus f prime 0, x. So it's going to be 1 time of x. Then plus f prime prime 0, which is going to be 1 over 2 factorial of x squared, plus f prime 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 0. So this divided by 3 factorial of x to the power 3 and so on. Since we have already gotten the first 4 terms, I don't really need to write down the rest of the terms here. This will give me a 1 plus x plus 1 over 2x squared plus 1 over 3x to the power 3 all the way to infinity. Next, okay, is a vectors question. Let's take a look at it. Okay, in question number 8, we are given line L1 as R1 is equal to 3, 2, 0 plus lambda of 2 minus 3, 1. And we are given L2 as R2. This is going to be equal to minus 4, 1 and minus 3 plus mu of 1, 2, and 4. So we are given this and we are supposed to impart A. Find the Cartesian equation of the plane that contains L1 and the point 1 minus 3 minus 1. Let me do a quick sketch of what is happening. So this, let's say, is that plane that is asked by the question. And this plane contains L1. So it is going to be this. And this plane also contains the point with coordinates of 1, minus 3 and minus 1. So in order for us to find the Cartesian equation of this plane, we need to first work out the normal vector to the plane. So for the normal vector to the plane, we are going to make use of vectors that are parallel to the plane. We actually already know one, because since L1 lies on the plane, so L1 will be parallel to 2 minus 3, 1, which means that 2 minus 3, 1 will also be parallel to the plane. So we do know one vector that is parallel to the plane that is required. Let's try to find another vector that is going to be also parallel to this plane but not parallel to this. So the other vector can be obtained by taking another point that is on L1. The most convenient point is by letting lambda be equal to 0. Then we will get another point as 3, 2, 0. So I'm going to make use of this. Okay, so if I were to connect this to this over here, this vector here is going to be also parallel to the plane. So let's try to find this vector. Okay, so it is going to be 3, 2, 0 minus away 1 minus 3 minus 1. This gives us a 2, 5, 1. Okay, so now 2, 5, 1 will be parallel to the plane, which means that the normal to the plane is going to be parallel to taking 2 minus 3, 1 cross 2, 5, 1. So this cross this will give us a minus 8, 0, 16. And this is going to be normal. This is going to be parallel to the normal to the plane. So this can be the normal to the plane also, but I'm going to use a simpler version by factorizing out 8, which will give me a minus 1, 0, 2. So I'm going to make use of this. Minus 1, 0, 2 will be the normal to the plane that I'm going to be using, which means that the equation of the plane is going to look something like this. R dot the normal, which I'm going to be making use of minus 1, 0, 2, is going to be equal to the position vector of a point that is on the plane. I can make use of this point, or any point that is on the plane. Let's just make use of this. So it will be 1 minus 3 minus 1 dot the normal minus 1, 0, 2. We have a minus 1 plus 0 minus 2. This is equal to minus 3. And replacing r by x, y, z, we will be able to get the Cartesian equation. So replacing r by x, y, z, x times this is going to be equal to this. Then plus 0 times this is going to be 0y. Then z times this is going to be 2z is equal to minus 3. So the Cartesian equation is going to be minus x plus 2z is equal to minus 3. Let's take a look at B. B is simple. For B, we just want to show that L1 and L2, they are perpendicular to each other. So I'm going to take the vector that is parallel to L1, dot the vector that is parallel to L2. If the result of the dot product is equal to 0, then I can say that L1 and L2 are perpendicular to each other. So let's take 2 minus 3, 1. This dot the vector that is parallel to L2, 1, 2, 4. Let's see what is the result. This will be 2 minus 6 plus 4, 0. Therefore, L1 is going to be perpendicular to L2. And yep, this is what the question wants us to show. So shown. C. Okay, C is going to be, C part 1 is going to be quite tedious. We want to find the values of lambda and mu such that R1 is going to be the one that is lying on here, minus R2, which is going to be the one that is here, is perpendicular to both L1 and L2. And we are supposed to state the position vectors of the points where this common perpendicular is going to be meeting L1 and L2. Let me erase this and do a quick sketch of the scenario that is asked in part C. So what that is mentioned in part C is something that is like this. Okay, I do need you guys to try to have a bit of visualization in terms of how I am actually trying to draw a 3D diagram, but I'm drawing it on the board, so it is actually a 2D board. Okay, but I'm going to try, and you try to visualize this together with me. So let's say here we have our L1, and coming down we have L2. Okay, and just to have the little bit of 3D effect, the shadow that L1 is going to be cast on the L2 plane can be something that is like this. Okay, so this is just a reference for us. So this is like L1 being cast on L2, and to just give a bit of a 3D effect. And if I were to join here to here, if I were to draw a line up from here to here, this will be the common perpendicular. Okay, this is what the question is trying to say. This is that common perpendicular, which means that it is the line that is going to be perpendicular to both L1 and L2 at the same time. And R1 is going to represent this point here. I'm going to call this point here R1. And this point here will be R2. So the question says that we are supposed to find the value of lambda and mu such that R1 minus R2 is perpendicular to L1 and L2. So it is this R1, it is this R2. And we are supposed to state the position vectors of the points, which is the position vector of R1, the position vector of R2. So let's just follow what the question says, okay? The question says we are looking at R1 minus R2. And we know what is R1, we know what is R2. So let's just find what is R1 minus R2 first. So this will be R1 is 3, 2, 0, then plus lambda, so 2 lambda, then lambda minus 3, so minus 3 lambda. Okay, this is weird. I'm going to erase this, then I'll have just lambda. So it will be this, minus away this, which is going to be equal to minus 4 plus mu, 1 plus 2 mu, and minus 3 plus 4 mu. So R1 minus R2 will be equal to 7 plus 2 lambda minus mu, and 1 minus 3 lambda minus 2 mu. 3 plus lambda minus 4 mu. So we have R1 minus R2 to be equal to this. And for a question that is like this, unless you have done it before, or else until this point, it is still going to be a bit confusing. Okay, and that is exactly what this question is trying to test us, whether we are able to navigate through a situation which is not exactly the clearest, okay, but are we able to trust our syllabus, trust what we have learned in order for us to make micro step forward. So what is the next micro step that we can make? The question did mention to us that R1 minus R2 is perpendicular to both L1 and L2. So I'm going to make use of this. Okay, I'm going to proceed according to the fact that R1 minus R2 is perpendicular to L1. Let me write it down here. If they are perpendicular, according to what we have learned in the syllabus, we can go for R1 minus R2. Since it's perpendicular to L1, so this dot 2 minus 3, 1, this should be equal to 0. Okay, so this is the first way that I'm going to continue. Another way that I'm going to be continuing is the fact that R1 minus R2 is also going to be perpendicular to L2. This is what that is mentioned to me by the question. So this is another micro step that I'm going to be taking. So the other one will be this. I'm going to write it down here. R1 minus R2. Okay, these are vectors. This dot 1, 2, 4. This should also be equal to 0. Let's plant the values in. Okay, so R1 minus R2, let's plant it in. So we will have here as a 7 plus 2 lambda minus mu, 1 minus 3 lambda minus 2 mu, and 3 plus lambda minus 4 mu. So this dot 2 minus 3, 1. This is equal to 0. Let's expand this. So this times this, we will have a 14 plus 4 lambda minus 2 mu. Then we will have this times this, which is minus 3 plus 9 lambda plus 6 mu. Then this times this will be a 3 plus lambda minus 4 mu. This is equal to 0, and I'm running out of space. Okay, I'm going to erase this and shift this over in a short while. So this will lead me to 14 plus 14 lambda is equal to 0. Nice. Because I'm going to be immediately solve for lambda. Lambda is equal to minus 1. So I'm going to continue with this. Okay, rather than shifting this, let me just draw a line here. Okay, so I'm going to again plant this in. It will be a 7 plus 2 lambda minus mu, 1 minus 3 lambda minus 2 mu, 2 plus lambda minus 4 mu. This dot 1, 2, 4, this is equal to 0. So we will have a 7 plus 2 lambda minus mu, then plus 2 minus 6 lambda minus 4 mu. Then we will have a 12 plus 4 lambda minus 16 mu. This is equal to 0. Simplifying this, we will have a 21 minus 21 mu is equal to 0. Again, we will be able to immediately quote for the value of mu. So lambda and mu has already been solved just because we are willing to take a bit of micro step. Okay, the last part is we are supposed to quote the position vector of the points where the common perpendicular meets L1 and L2. So we are supposed to quote the position vector of R1 and the position vector of R2. And at R1, we have just solved for it because R1 is a point that is lying on L1, and we know what is the value of lambda that caused R1 to happen, which means that at R1, lambda is equal to minus 1. The same idea is going to be applied to R2 because for R2, which is lying on L2, it is dependent on mu, and we know that mu is going to be equal to 1. So this is happening, which can allow me to find the position of R1. So let me write position vector of R1. Okay, so it is this OR1. OR1 will be 3, 2, 0 plus lambda, which is minus 1 of 2 minus 3, 1. So OR1, this is equal to 1, 5, and minus 1. And as for OR2, the other position vector that the question is asking for, I'm going to make use of mu and plug it into this equation of the line L2. So OR2 will be minus 4, 1, minus 3 plus mu is 1 of 1, 2, 4. So this is going to be equal to minus 3, 3, and 1. And the very last part of the question, C part 2, asks us to find the length of this common perpendicular. It is this. So it is just basically going to be the modulus of R1 minus R2. So for the last part of C, let's just simplify what is R1 minus R2 when lambda is equal to minus 1 and mu is equal to 1. So it is going to be R1 minus R2 will be 7 plus 2 times of lambda. Lambda is equal to minus 1. So minus 1 minus mu is equal to 1. Then after that, 1 minus 3 times of minus 1 minus 2 times of 1. Then 3 plus lambda, which is minus 1. Then minus 4 times of 1. So R1 minus R2 is going to be equal to 4, 2, minus 2. And now we can find out what is the required length, which is the modulus of R1 minus R2. So it's going to be square root of modulus of this, 4 square plus 2 square plus minus 2 square. This is going to be square root of 24, or you can also write this as 2 square root of 6. Okay, we are moving on. Okay, I think so far it seems to be pretty okay still. Let's take a look at question number 9. Okay, now question number 9, we are given the function f(x). Let me write it down here. F(x) is e to the power of x cosine x when x is going to be between 0 and half pi, or pi over 2. Part A, we are supposed to be using calculus. Actually, why did the question say calculus? Of course, it is because if they don't mention the word calculus, we can actually solve part A by pressing this function into the graphing calculator and search for where are the stationary points, and we can use our observation to determine the nature of this stationary point. But sadly, we can't do that here in part A. We are supposed to use calculus. So to use calculus to determine the stationary points and to determine the nature of to find the stationary point and to determine the nature of the stationary point, we are going to make use of f prime x, and then we are going to make use of f prime prime x to determine the nature of the stationary point. So for part A, let's first find f prime x, and that will be e to the power of x minus sine x plus differentiating e to the power x is still going to be e to the power x cosine x. So factorizing out e to the power x, we will have a e to the power of x, then cosine x minus sine x. Let's find f prime prime x. So differentiating this, e to the power x, I will let it be. I'm going to differentiate this, which is going to be giving me a minus sine x minus cosine x, plus differentiating e to the power x is still going to be e to the power x, and this here is going to be equal to cosine x minus sine x. Let's combine this together, and we'll have this, which will be minus 2 sine x minus cosine plus cosine x is going to disappear. So it will be e to the power of this times this. So let me just rewrite this. So this will be minus 2 e to the power of x sine x. Okay, this is going to be the f prime prime x. So to find the stationary point, that is when f prime x is equal to 0. So I'm going to let f prime x be equal to 0, which is going for e to the power of x cosine x minus sine x here to be equal to 0. And for e to the power of x itself, it is always going to be positive. So it is impossible for e to the power x to give me a 0. So that leaves me with cosine x minus sine x to be equal to 0. So sine x is going to be equal to cosine x. Dividing this across, we have a sine x over cosine x to be equal to 1, which means that tangent x is going to be equal to 1. And let's not forget that x is a number that is between 0 to pi over 2. So what is the value of x that will cause tangent of that number to be equal to 1? X is going to be equal to pi over 4, one of our special angles. So we have determined the x coordinate of the stationary point. We also want to determine the y coordinate of the stationary point, and that will be f of pi over 4, or 1/4 pi. So let's substitute it in here. This will be e to the power of pi over 4 cosine of pi over 4. Cosine pi over 4 is 1 over square root of 2. So this will be 1 over square root of 2 e to the power of pi over 4. So the coordinates of the stationary point will be pi over 4, 1 over square root of 2 e to the power of pi over 4. Its nature can be found by working on the value of f prime prime pi over 4. Let's try. F prime prime pi over 4. This is going to be equal to minus 2 e to the power of pi over 4. Then sine of pi over 4. Sine of pi over 4 is positive. E to the power of pi over 4 is also positive. Negative 2 is negative, which means that this is less than 0. The second derivative is less than 0. That tells me that this stationary point is a maximum point. Let's write it down here. Therefore, the stationary point is going to be at pi over 4 and 1 over square root of 2 e to the power of pi over 4. And this is a f prime prime is less than 0. This is a maximum point. Okay, this is A. Let's take a look at B. Okay, I will need some space for B. Let me erase this. Okay, so for B, we are supposed to apply integration by parts. And we have this integrating e to the power of 2x cosine 2x dx. And we're going to make use of LIATE according to what we have learned in our syllabus. E to the power of 2x, I'm going to see this as e. Then this cosine, I'm going to see it as t. And according to LIATE, t comes before e. So we will let u be equal to this cosine 2x. And dv dx, I'm going to let it be e to the power of 2x. So based on this, I'm going to find du dx. Du dx is going to be minus 2 sine 2x. Then v here is going to be 1 over 2 e to the power of 2x. So this is going to be equal to uv half e to the power of 2x cosine 2x minus integration of v multiplied by du dx. So minus, I'm going to take it out, it will become plus. 2 multiplied by half is going to become 1. So we are going to be left with e to the power of 2x sine 2x dx. And in order for me to continue to integrate this, I'm going to apply integration by parts one more time, and especially when that is the hint that is given to us by the question. So let's try to integrate this by parts again. Integrating this by parts, I'm going to make use of LIATE, seeing this as e, and seeing this once again as t. T comes before e in our acronym LIATE. So we will be letting u be equal to sine 2x, and dv dx, this is going to be e to the power of 2x. So du dx here is going to be 2 cosine 2x, and v here is 1 over 2 e to the power of 2x. So this is going to be equal to 1 over 2 e to the power of 2x cosine 2x plus, here we are going to apply another round of integration by parts. So it's going to be uv, we'll have a half e to the power of 2x sine 2x minus integration of v du dx. 2 multiplied by half is going to become 1. So this will be e to the power of 2x cosine 2x. We will have this. Let me rewrite this together with this in one row again. Or maybe let me just be a bit lazy and write this down here. Okay, so if I were to write this down here, we will have an integration of e to the power of 2x cosine 2x dx is equal to this. And we are seeing the integral repeating. So I'm going to move this over to the left-hand side. So let's move it over. So we have an integration of e to the power of 2x cosine 2x dx. With this being moved over plus another e to the power of 2x cosine 2x dx. This is going to be equal to this. I'm going to factorize out half e to the power of 2x, which will then leave me with a sine 2x plus cosine 2x. And this can be combined into 1, 2 times of e to the power of 2x cosine 2x dx. This is equal to 1 over 2 e to the power of 2x sine 2x plus cosine 2x. And now I'm going to divide throughout by 2 definitely, so that this can become the subject. Integration of e to the power of 2x cosine 2x dx is going to be equal to 1/4 e to the power of 2x sine 2x plus cosine 2x. Let's not forget about the arbitrary constant plus c. So this is what we are getting for B, and let's move on to the last part, C. So for this last part, part C, we are supposed to look at this again, and this is now going to be rotated completely about the x-axis. We are supposed to find the exact volume that is generated. What is the first thing that we should do? We should try to sketch the graph of this. So let me show you the graph. I've already sketched it onto my GC, my graphing calculator, and the graph looks like this. Here, you'll go up, and you'll come back down here, from 0 all the way until 1 over 2 pi. So this portion of the graph here is going to be rotated. This portion of the graph is going to be rotated about the x-axis. Okay, this is the graph of y is equal to fx. And we are supposed to find the volume. Yep, we are supposed to find the exact volume when this region here is being rotated. So the volume is going to be integrating from 0 to half pi of fx square. Let me write it down. So it is this, fx square dx. So to integrate this, I'm going to continue by taking out pi, then integrating from 0 to half pi here. This square is like having this e to the power of x cosine x square dx. Okay, it seems really like a question which I'm going to be making use of the previous part, okay, because a lot of things that is from the previous part, a lot of things that is from the original fx and part A, part B, you know, they seem to be surfacing. So let's watch out for times when I can make use of the previous few results. This is equal to pi 0, 1 over 2 pi. We have a e to the power of 2x, okay, this has appeared in the previous part. Then this, sadly, it is cosine square x. This has not appeared in the previous part, but we can transform this so that it looks like what we have in the previous part, because we can make use of trigonometric identity. The trigonometric identity that I'm going to make use of will be this. Cosine 2a, this is equal to 2 cosine square a minus 1. So cosine square a, this is going to be equal to cosine 2a plus 1 divided by 2. So I shall apply this to here, which will help me to change this to e to the power of 2x. E to the power of 2x. This will be changed according to this. So this will be changed to cosine 2x plus 1 divided by 2. Okay, so we will have this. And now we can actually start to try make use of the previous result. 1 over 2, I'm going to take it out of the integral. This gives me a pi over 2, integrating from 0 to half pi. Then we will have a e to the power of 2x multiplied by this, which is cosine 2x. Nice. This is something that we have integrated previously, right? So this plus e to the power of 2x, this multiplied by 1 gives me e to the power of 2x. And this is no problem because we have actually know how to integrate this. This is a secondary school kind of integration. So we have this dx, which means that it is going to be equal to pi over 2. Integrating this e to the power of 2x cosine 2x, we have the result from the previous part, and which is the one that we have shown in part B. So I'm going to use exactly that result, and that will be 1 over 4 e to the power of 2x sine 2x plus cosine 2x. And of course, I'm going to ignore the plus c because now we are doing a definite integral. And integrating this, it is going to be equal to 1 over 2 e to the power of 2x with a lower limit of 0 and an upper limit of half pi. And now let's substitute this in. So substituting this in, the upper limit in, pi over 2. Okay, let's try to substitute this in. We'll have a 1 over 4 e to the power of 2 times of this, which is going to be e to the power of pi. Then sine of 2 times of this, which is going to be sine pi plus cosine pi plus this will be half e to the power of 2 times of this is going to be pi. So we have this minus away, substituting 0 in. Substituting 0 in, it is going to give me a 1 over 4 e to the power of 0. Then we will have a sine 0 plus cosine 0, then plus half e to the power of 0. We can definitely be evaluating some of them. For example, like this. This here is equal to 0. This here is equal to minus 1. This I'm going to leave it. This is going to be equal to 1, just like this. This is going to be equal to 1. This is going to be equal to 0. And cosine 0, this is equal to 1. So if you were to work this out, you will be getting this. Let me just write it down for you. So we will be getting pi over 2 of this will become minus 1 over 4 e to the power of pi plus 1 over 2 e to the power of pi. Then minus away this will become 1 over 4 plus 1 over 2. So this will be equal to pi over 2, 1/4 e to the power of pi minus 3/4. We can leave it as this, or we can also factorize out 1/4, giving me my final answer as pi over 8 e to the power of pi minus 3. Okay, this is question number 9. Let's move on to question number 10. Question number 10 is the second last question that we're going to be dealing with. Okay, let's take a look at question number 10. Okay, now let's take a look at question number 10, part A. In this part of the question, we are dealing with the number of bacteria. It is given to us as n, and we are told that the growth rate of the number of bacteria is Kn, and that's it. Okay, and K is a positive constant. So in part A, this is what I'm going to do. I'm going to just follow what the question says, because the growth rate is going to be equal to Kn, where K is a positive number. And we are supposed to write down the differential equation that is involving n, t, and k. So I guess I've done that. We are supposed to find k and also the time that it takes for the number of bacteria to reach 1,000. So in order for us to find the time for n to be equal to 1,000, we need an equation not as this, but it is going to be in the form of n to t. So we need to solve this differential equation. This is a variable separable kind of differential equation. So I'm going to bring n over to the left-hand side by dividing it across to give me this. T, this is equal to a constant k. Integrating both left and right hand side with respect to t, we will get a 1 over n. This is dn. This k is a constant, so I'm going to take out of the integration notation, which gives me this. Integrating this is ln modulus of n. It's going to be equal to kt plus an arbitrary constant. I'm going to go for a as the arbitrary constant. Removing ln on the left-hand side, we have a modulus of n is going to be e to the power of this, which I'm going to write it as e to the power of a, e to the power of kt. Removing the modulus, n here is going to be equal to plus or minus e to the power of a, e to the power of kt, and I'm going to just group this as a single arbitrary constant b, e to the power of kt, where b is representing this plus or minus e to the power of a. Let's try to solve for b, and hopefully we can also try to solve for a. The question did tell us some information. Let's try to make use of them. The question tells us that initially there are 100 bacteria. Initially means t is equal to 0. 100 bacteria means n is equal to 100. So I'm going to make use of this piece of information. When t is equal to 0, n is equal to 100. So making use of this, I will have b e to the power of t is equal to 0. This is equal to 100. Therefore, we know that b here is positive 100. Let me rewrite this. So n is going to be equal to b, which is 100 e to the power of kt. Let's make use of the other piece of information that is given to us, which is there are 300 bacteria found at a time when t is equal to 2. So when t is equal to 2, n is found to be equal to 300. So 100 e to the power of 2k, this is equal to 300, means e to the power of 2k, this is going to be equal to 3. 2k, this is equal to ln 3. So k is now solved to be half of ln 3. We are supposed to, are we supposed to end here? We are supposed to continue. We are supposed to find the time that it takes for the number of bacteria for n to reach 1,000. So after I found this, I'm still going to go for one more step, and that is when n is equal to 1,000. Okay, so, I probably should try to make use of this to sub it back into the original ones. Okay, so let me do it here. N here is equal to 100 e to the power of kt. Okay, let's do a little improvisation also. Of course, we can just replace this k by half ln 3. Or we can also try to make use of this. Okay, let me mark it down. I can try to make use of the fact that e to the power of 2k is equal to 3. I think this will make our solution even more, let me choose a word to use, more slick. Okay, so if I were to do that, this will be 100, then e to the power of 2k to the power of t over 2, right? Because this to the power of t over 2 is like 2k multiplied by t over 2, which will give me kt. And this is 3. So we have 100, 3 to the power of t over 2. Such a nice and slick and lean equation that I have in terms of n and t. So I'm going to make use of this here. So n is equal to 1,000, which means that 100, then 3 to the power of t over 2. This is equal to 1,000. Okay, n is equal to 1,000. I'm going to try to solve for t now. So dividing this across to the other side, 3 to the power of t over 2, this is equal to 10, which means that if I were to ln both sides, t over 2 ln 3, this is equal to ln 10. So t is going to be equal to 2 times of ln 10 divided by ln 3. This is equal to 4.19. So this is part A. Let's move on to part B. And now in part B, there is not just going to be the rate of growth of the number of bacteria, there is also going to be a rate of decrease in the number of bacteria. So if I were to, in part B here, look at it from the system point of view, then to create a dn dt, we need to look at not just growth, but also decrease. According to the question, the growth rate is kn. According to the question, the rate of decrease is d, which means that dn dt is now going to be the rate of increase, which is kn, minus away the rate of decrease, which is d. And we're supposed to form a differential equation and then solving for it to get t in terms of n and d. So what we have now here is a variable separable again. I'm going to divide this across to the other side. We have a 1 over kn minus d, dn dt, this is equal to 1. I'm going to integrate both the left and the right hand side with respect to t. But because the question wants t in terms of n and d, I'm going to write this on the left hand side instead. So integrating 1 with respect to t is going to be just this. And integrating this with respect to t is going to be 1 over kn minus d dn. So on the left hand side here is going to be just t, and here is going to be 1 over k of ln modulus of kn minus d plus an arbitrary constant. I'm going to go for c as the arbitrary constant. And let's not forget about what is k. K we have actually solved in the previous part. In the previous part, k was half ln 3. So let's replace this k by half ln 3. So this is going to be equal to 2 over ln 3. Then ln of modulus of k, replacing it by half ln 3 will give me a half n ln 3 minus d modulus of it. This is going to be plus c. So we need to still solve for plus c because t is going to be in terms of just n and d. So to solve for plus c, we are going to make use of this piece of information, which is initially the number of bacteria is still going to be equal to 100. So when t is equal to 0 initially, we are told that n is still going to be equal to 100. So substituting it into here, we have a 2 over ln 3, ln of half multiplied by n, which is now going to be 100, ln 3 minus d, then modulus of this plus c, this is equal to t, t is equal to 0. So this gives us c to be equal to minus 2 over ln 3, ln of the modulus of 50 ln 3 minus d. So c is equal to this, which means that t is going to be equal to 2 over ln 3, ln modulus of half n ln 3 minus d plus c, which is minus 2 over ln 3, ln modulus of 50 ln 3 minus d, which I can definitely group this together using law of logarithmic, which is going to be 2 over ln 3, factorizing this out. We will have a ln of this minus away ln of this, which can become a ln of half n ln 3 minus d over 50 ln 3 minus d. I can leave it as this, or I can just multiply the numerator and the denominator within this modulus by 2. It sort of like looks nicer, I guess. So this will be n ln 3 minus 2d over 100 ln 3 minus 2d. So this is t in terms of n and d. But the strange thing about this question is that it asks us to hence find n in terms of t and d. So we just need to re-express this and make n the subject. So I guess let's do that. So if I want to make n the subject, okay, so let me rewrite this again. So we have a 2 over ln 3, ln of modulus of n ln 3 minus 2d over 100 ln 3 minus 2d. This is supposed to be equal to t. Let's shift this over to the right-hand side. So we have a ln of modulus of n ln 3 minus 2d divided by 100 ln 3 minus 2d is going to be equal to t over 2 ln 3, which I can also write it as ln 3 to the power of t over 2. So ln of this is equal to ln of this. This tells me that within ln, it is this 3 to the power of t over 2. This is going to be equal to n ln 3 minus 2d over 100 ln 3 minus 2d. I'm going to remove the modulus, okay, because 3 to the power t over 2 is going to be positive all the time. So I'm going to have this as this, and I'm going to now make n the subject. Okay, this I'm going to multiply across the other side, n ln 3 minus 2d. This is going to be equal to 100 ln 3 minus 2d, then 3 to the power of t over 2. 2d, I'm going to bring it over to the other side. Let me be a little bit lazy. So plus 2d, I'm going to just erase this, okay? So we have n to be equal to this divided by ln 3. So it is going to be equal to 100 ln 3 minus 2d. Then this 3 to the power of t over 2 plus 2d divided by ln 3. I can leave it as this, or I can also try to factorize out 2 from the numerator, which will then give me a 2 over ln 3 of, this will be a 50 ln 3 minus d, then 3 to the power of t over 2 plus d. Okay, this is n in terms of now d and t, okay? Then the last part of this question, last part is part C. Find the range of values of d for which the number of bacteria will decrease. Okay, actually, personally, I find this C part 1 pretty interesting. You need quite a lot of, you need more deduction. Okay, so I did try to think a little bit on how I can do this C part 1, especially when it is just a 1-mark question. So if we were to use the more traditional way as in like if we were to use differentiation, because differentiation can help me to find when n is decreasing. So I basically just need to let n dt be less than 0, then n will be decreasing, but that will make it very, very complicated. So what I'm going to try do is to look at n over here. Let me show you what I mean. Let me erase this. Because the question did tell me to express n in terms of d and t. So, and in this last part here, d is actually given to me as d has been a constant all along, okay? Which means that I can, if I were to expand this, I will get a 2 ln 3 multiplied by 50 ln 3 minus d. Okay, this is just a constant. Then this to the power of t over 2 plus this multiplied by this. So it's going to be 2d over ln 3. And because d is a constant, I can see this as just simply p, 3 to the power of t over 2 plus another constant q. And if you were to think about the graph, of constant to the power of a variable, then this 3 to the power of t over 2 is going to be an exponential-like looking graph. It's going to be a graph that is like this. Right? It is going to be this. This is something that we have learned since our secondary school. E to the power x is an exponential graph. 3 to the power t over 2, it will also be an exponential graph. And this q will cause the graph to shift up and down, to translate up and down. So it's not going to cause n to be increasing or decreasing. N will still be increasing, provided that the coefficient is positive. And the moment when the coefficient is negative, then this entire graph will be reflected about the horizontal axis. So the graph will become, the moment when p is negative, okay, then the graph will become this way. Right? Then it will become a decreasing graph. And that is what I need. If I can just base on my observation of the coefficient of 3 to the power of t over 2, then we can actually work out when n will be decreasing, and that will be way faster. And I think that will be how we are going to be scoring the 1 mark in C part 1. So let me write it down here, C part 1. I'm going to let the coefficient of 3 to the power of t over 2, which is this, okay, which is this thing here. So I'm going to let this 2 over ln 3 of 50 ln 3 minus d. I'm going to let this be less than 0. I'll let this be a negative number. So if I were to let this be a negative number, this disappear. We have a 50 ln 3 minus d is less than 0. So my answer is just simply d to be bigger than 50 ln 3 for C part 1. As for C part 2, we are going to take d to be equal to 58. We want to find the time for the number of bacteria to reach 0. So we do have the time in terms of n and d is going to be equal to 58. So let's try part 2. We're going to try to find t when n is equal to 0. So I'm going to be letting n to be equal to 0. And by letting n to be equal to 0, the number of bacteria to be equal to 0, and d to be equal to 58, we will have t to be equal to, making use of this, 2 over ln 3, ln of modulus of 0, multiplied by ln 3 minus 2 times of d, which is 58, divided by 100 ln 3 minus 2 times of d, which is 58. Modulus of this, if I were to press this into the calculator, taking into account the modulus, this is equal to 5.35. Okay, now we are going to move on to the last question, question number 11. It is here. It is this question here. Okay, let's take a look at this question together. Okay, in question number 11, I've done a sketch for myself to discuss with you guys about the question also. In part A, we want to find, in terms of A and beta, the distance PS. And the question told us that at point Q, theta is equal to beta. Let me write down this piece of information also. This is good information that I'm going to be making use of. So at point Q here, theta is equal to beta, and at point R over here, okay, at this point here, theta is going to be equal to 2 pi minus beta. So in part A, we want to try to find PS. PS is going to be this distance to this distance. So we can just simply make use of the x coordinate of this minus away the x coordinate of this. So let's start that by making use of the fact that theta is equal to beta here to find x coordinate here. So at point P, which is going to share the same x coordinate as point Q, theta is equal to beta. So x is going to be equal to a of beta minus sine beta. Okay, replacing all the theta here by beta. I'm going to do the same thing for point S. So at point S, the x coordinate is the same as the x coordinate for R, and at point R, theta is equal to 2 pi minus beta. So theta here is 2 pi minus beta, which means that x is going to be equal to a times of theta, which is going to be 2 pi minus beta minus sine of 2 pi minus beta. And what is sine of 2 pi minus beta? Again, we are going to make use of trigonometric transformation. So we have learned that in secondary school, sine of 2 pi minus an angle is going to be minus sine of the angle. So by making use of this, we can now re-express what we have here. This is going to be equal to a of 2 pi minus beta. Sine 2 pi minus beta is going to be equal to minus sine beta. Minus times minus is going to become a plus. So we have a plus sine beta over here. So now we can find PS. PS is going to be the x coordinate at here minus away the x coordinate at here. So the x coordinate at here is going to be this a, 2 pi minus beta plus sine beta, minus away the x coordinate here. So that will be a beta minus sine beta. This PS will become a of 2 pi minus 2 beta plus 2 sine beta, which is equal to 2a of pi minus away beta plus sine beta. Okay, and next we want to try to find the area of the shaded region that is on the diagram and represent the area that is under the bridge, and we want to show that that area is equal to that expression there. So we are talking about this area here, this region. And to integrate this, we are going to make use of, to find this area, we are going to make use of integration. The solution is a little bit long, so let me just erase this first, okay? So in part B, the area is going to be this region here, and we have mentioned it a lot of times, especially on Achevas TV in our theory outline. When you're trying to find area, you don't want to just simply code the formula based on the parametric, based on the parameters. Okay, you want to code the area based on an integral that is with respect to x. Okay, because that is what you can see here, not theta. Theta, you cannot physically see what is happening, but x you can, which means that based on what we have here, the area will be integrating from here, which is going to, I'm going to call it just x cube. Okay, here is x cube all the way until here. I'm going to call this xr of y dx, because by doing so, I know since my secondary school that this represents this area here. Then we will do our own substitution. So, for example, x cube is here. That is when theta is equal to beta. So x cube, I'm going to replace it by beta. xr is when theta is equal to 2 pi minus b. So here, okay, I'm going to replace by its corresponding theta. This is going to be 2 pi minus beta. So y is this here. I'm going to do my own replacement. So y is a of 1 minus cosine theta, and dx, in order for me to replace dx, I'm going to take x and I'm going to differentiate it with respect to theta. So dx d theta, this is equal to a of 1 minus cosine theta. So dx here, I'm going to replace it by a 1 minus cosine theta d theta. We will always make sure that we start with this. It is a good habit. It is also going to be more consistent when we try to find the area where the curve is defined for us parametrically. So now we have the parametric form. Okay, and we visualize it from the Cartesian form. Now from the parametric form, we are going to continue with our integration as per usual. So this a, I'm going to take it out. It will be a squared. I'll be integrating from beta to 2 pi minus beta of 1 minus cosine theta square. I'm going to expand this. So we have a square integrating from beta to 2 pi minus beta. Expanding this gives me a 1 minus 2 cosine theta, then plus cosine square theta d theta. This is fine for me to do my integration. This is also fine. For this, I'm going to try to do a bit of manipulation to it by making use of what we have learned in our trigonometric identities. And the identity that I'm going to be making use of will be this cosine 2a is equal to 2 cosine square a minus 1. We have used it in the previous question. And this tells me that cosine square a is going to be equal to cosine 2a plus 1 divided by 2. Okay, let me make use of this. So let me rewrite this. This will be a squared integration from beta to 2 pi minus beta of 1 minus 2 cosine theta plus this, which I'm going to replace it by cosine 2 theta plus 1 divided by 2 d theta. I am going to factorize out half, which will then give me a square, half a square integration from beta to 2 pi minus beta of 1 minus away, sorry, if I were to factorize out half, then this 1 here will become 2. So we have a 2 minus away 4 cosine theta plus cosine 2 theta plus 1. 1 and 2, they will be combined to become 3. So I'm going to just write it as 3 here, okay? So this will become a 3, then this will disappear. So this is what I'm supposed to be integrating. And it feels pretty okay because we have a half a square here. And what I'm supposed to be showing indeed has a half a square here. So let's see whether the rest of the parts will end up with this over here. So let's continue with the integration. Let me continue with it here. So half a square, this is good. The rest of the terms here, if I were to do my integration, they will become 3 theta. It's from here. Minus away 4 sine theta. That is integrating this. As for this is going to be plus 1 over 2 sine 2 theta. The lower limit is going to be beta. The upper limit is going to be 2 pi minus beta. Now let's substitute the lower and upper limit in. So we will have a half a square. And here we will have a 3, this substituting in, 2 pi minus beta minus 4 sine 2 pi minus beta. We will need to do a trigonometric transformation. Then plus half of sine of 2 times of this, 4 pi minus 2 beta. Again, another transformation that's going to be happening. Minus away, substituting beta in, we have a 3 beta minus 4 sine beta plus half sine 2 beta. Okay, so we have this. Simplifying this further, half a square, and applying the trigonometric transformation, what we will be getting here is going to be 6 pi minus 3 beta plus 4 sine beta minus half sine 2 beta. Okay, minus away this is going to be equal to 3 beta minus 4 sine beta plus half sine 2 beta. And now we can combine this further. And combining this will give us our final answer. In fact, we will be getting a 6 pi minus away 6 beta plus 8 sine beta minus sine 2 beta. And this is what the question wants me to show. So this part here is done. I'm going to find the next part. The next part is actually pretty okay. Part C, let me just do it here. For part C, it is now given to us that the area, which is this that we have found, under the bridge is going to be 7.8159 squared. Find the value of beta. So we are going to be letting this half a square, 6 pi minus 6 beta plus 8 sine beta minus sine 2 beta be equal to what the question has given to me, which is 7.8159 squared. And the a square can be cancelled. And I think I'm going to bring everything over to the left-hand side. Okay, I think it will be easier for me to solve it because I'm going to be sketching the graph of this onto my graphing calculator and solve it by using the graph. So I'm going to bring this over to the left-hand side, which will give me a half of 6 pi minus 6 beta plus 8 sine beta minus sine 2 beta minus away 7.8159 is equal to 0. So I'm going to sketch the graph of the left-hand side with beta pressed in as x on my graphing calculator, and at the place where the graph intersects the x-axis, intersects the horizontal axis, will give me the value for beta. So if I have done that from my graphing calculator, I will be able to get the value of beta. Beta is going to be 1.90. Next, part D, the last part of the question. Given that the width PS was what we have found in the first part, is 50. Find the greatest and the least possible height of the arc QR above the expressway. So the greatest and the lowest part of the arc will be either, the lowest part will be either Q or R. The highest part is definitely going to be this part. Okay, so let's try to work on the y coordinates of Q and R, and let's see which one is lower. And then we will try to find the stationary point here and then work on the y coordinates of the stationary point. Okay, so for part D, we are given that PS is equal to 50. So PS here is equal to 50, and we have found what is PS in the previous part. That was 2a pi minus beta plus sine beta. So this is equal to 50, and we also found the value of beta from part C. So let me make use of that same value of beta. So this pi minus beta from part B to making use of the 5 significant figures value for beta is going to be 1.9000. Okay, actually it's not much of a difference, but I'm going to make use of 5 SF for intermediate values. So we have this is equal to 50. This will help me to solve for A. A is going to be equal to 11.427, again, to 5 significant figures. So by making use of A, we will now know what is Y in terms of just theta, because A is already solved for this. So let's try to find the value of Y for Q and for R. So at the point Q, let's check. So at point Q, theta is going to be equal to, according to the question, beta. So theta is going to be equal to 1.9000. So Y will be A, which is going to be this. So 11.427 of 1 minus cosine of theta, which is 1.9000, which is beta. So this Y value is 15.1. Let's try to match and check whether it is going to be higher or lower than the Y coordinates at point R. So at point R, theta is going to be equal to 2 pi minus beta. This was given to us by the question. So 2 pi minus away 1.9000. So the Y coordinates will be equal to A, which is going to be 11.427. 11.427, then 1 minus cosine of the angle, which is now going to be this. So 2 pi minus 1.9000. Pressing this into the calculator, this is also going to be equal to 15.1. So this gives us the least possible height. So therefore, now we know the least possible height of the arc is going to be equal to 15.1. Let's now try to find the highest possible point. Let's try to find the greatest height of the arc. So the greatest height is going to be here. We can see that is when a turning point is occurring. So let's try to find dy dx. We have already found dx d theta just now. I've erased it, but dx d theta was a1 minus cosine theta. And we can easily find dy d theta, that is going to be equal to a. And differentiating this, we are going to be getting a positive sine theta. So we can find dy dx now. Dy dx is dy d theta divided by dx d theta. So that is going to be equal to a sine theta over a of 1 minus cosine theta. So differentiating this, dy d theta, this is differentiating this is going to be equal to a can be cancelled. We will have a sine theta over 1 minus cosine theta. And since we are working on the maximum possible point, we are going to let dy dx be equal to 0. And this tells me that it is going to be sine theta over 1 minus cosine theta to be equal to 0. So sine theta is equal to 0. And theta is a value that is between 0 to 2 pi. So for sine theta to be equal to 0, theta will be either 0 or pi or 2 pi. When theta is equal to 0, it is actually somewhere to the left-hand side. When theta is equal to 2 pi, it is actually going to be somewhere that is on the right-hand side of here. So in between here, it has to be equal to this. So we are going to take theta to be equal to pi, and that will help us to work on the y coordinates at the point where the greatest height, okay, the point where the greatest height occur. So at the greatest height, we know that now from our deduction, theta must be equal to pi. So y is going to be equal to a. Let's not forget, a is equal to 11.427. Then 1 minus cosine of pi. And this will give me 22.9.